How long would it really take to leave our solar system? Not just to sail past Pluto or wave goodbye to Neptune, but to truly cross the invisible frontier where the sun's reach fades into the eternal night between the stars. This is not an easy question, because to leave the solar system means to measure distances so vast that they begin to lose meaning, and timescales so immense they stretch beyond our imagination. Yet today, we'll try to answer it, with real numbers, human stories, and a bit of wonder. By the end of this journey, you'll see why leaving the solar system is, at the same time, simpler than it sounds, and far harder than it seems. Before we can talk about the time it takes to leave, we have to define what leaving even means. Space, unlike Earth, has no borders. There is no gate labeled, "You are now leaving the solar system." Instead, our cosmic neighborhood fades gradually into interstellar space, like the colors of a sunset melting into twilight. There are at least 3 ways to define where "out there" begins, and each tells a different story about our place in the universe. The first definition is the simplest: leaving behind the orbits of the known planets. When you pass beyond Neptune and Pluto, you step beyond the region where the planets circle the Sun, roughly 50 astronomical units, or AUs, away. In that sense, you could say you've left the solar system once you're beyond Pluto's reach, though the Sun's gravity still grips you tightly. The second boundary is more scientific: the heliopause, the point where the solar wind, a river of charged particles flowing from the Sun, finally collides with the wind from other stars. Inside it, space is still under the Sun's influence. Outside it, the interstellar medium begins. It's the true frontier between the Sun's domain and the galaxy beyond. And then, there's the third, most extreme definition: the Oort cloud, the Sun's final gravitational frontier. This vast, distant sphere of icy debris may extend out to 100,000 Australian dollars, 100,000 times the distance between Earth and the Sun. Beyond it, the Sun's gravity finally loses its hold, and the traveler belongs not to our solar system anymore, but to the galaxy itself. To make sense of such distances, we need to shrink them down. 1 astronomical unit, 1 AU, is 150 million kilometers. The average distance from Earth to the Sun-Pluto's orbit lies between 30 and 50 Australian dollars. The heliopause sits around 120 Australian dollars. And the Oort cloud begins perhaps 2,000 Australian dollars away, and might stretch to 100,000 Australian dollars. If the solar system were a city, Pluto would be your front gate, the heliopause the end of your neighborhood, and the Oort cloud the national border. Beyond that border lies interstellar space, a wilderness so vast that even light needs over a year to cross it. But distance means little without speed. Let's talk about how fast we can go. A commercial airplane cruises at around 900 kilometers per hour, not even close to a crawl. Earth itself travels around the Sun at 30 kilometers per second, nearly 108,000 kilometers per hour. These are impressive by human standards, but in the solar system, they are small steps. Our most ambitious spacecraft, however, tell a different story. The New Horizons probe, which gave us our first close look at Pluto in 2015, left Earth traveling about 14 kilometers per second relative to the Sun. The legendary Voyager 1, launched in 1977, is moving at 17 kilometers per second and is still drifting farther away. And then, there's NASA's Parker Solar Probe, the fastest human-made object in history, which reached a breathtaking 200 kilometers per second, but only while orbiting close to the Sun. It isn't escaping the solar system. It's dancing around its heart. So how long would it actually take to leave? Using the first definition, to pass the region of the planets, beyond 50 Australian dollars, a well-planned probe can do it in just over a decade. New Horizons reached Pluto, about 32 Australian dollars away, in 9.5 years. If it continues at its current pace, it will cross $50 in about 12. But if we define leaving as crossing the heliopause, the edge of the sun's protective bubble, we must think in decades. Voyager 1 reached that boundary in 2012, 35 years after launch, at a distance of $121. Voyager 2 followed 6 years later, at $119. Both probes, now in interstellar space, are still faintly whispering back to Earth from more than 20 billion kilometers away. And what about truly escaping the sun's gravity, passing through the Oort cloud and out into the Milky Way? That's where the timescales become almost incomprehensible. The Oort cloud's inner edge lies around $2,000 away. At Voyager's pace of roughly $3.60 per year, it would take about 550 years just to reach it. To travel beyond the outer edge, $100,000 would take 20,000 to 30,000 years. For perspective, that's longer than all of recorded human history. If our species vanished tomorrow, the Voyagers would still be traveling in silence, crossing the darkness long after our languages, our music, and our monuments had turned to dust. So can we go faster? Could a human crew ever make the journey? Let's look at our options. With today's chemical rockets, the kind that power most of our launches, we've already reached their limits. They're perfect for escaping Earth's gravity well, but terrible for long interstellar voyages. The problem is fuel. The more you carry, the heavier you become, and the harder it is to accelerate. Even with gravitational boosts from Jupiter or Saturn, we can barely exceed 25 kilometers per second. That's fast enough to leave the region of the planets, but not nearly fast enough to escape the sun's gravity in a meaningful time frame. Enter nuclear thermal propulsion, a technology that uses nuclear reactors to superheat hydrogen and expel it for thrust. Such rockets could reach speeds of 40 or 50 kilometers per second, about twice as fast as Voyager 1. That would cut the trip to the heliopause down to about 15 or 20 years. But even then, reaching the Oort cloud would take centuries. Then comes Project Orion, one of the most ambitious and controversial designs ever conceived. Born in the 1960s, Orion proposed using small nuclear explosions detonated behind a reinforced pusher plate to propel a spacecraft forward. It sounds outrageous, but it could, in theory, reach 100 kilometers per second or more, enough to cross the heliopause in just 6 years, and the inner Oort cloud in under a century. But detonating hundreds of nuclear devices in space isn't exactly ideal, politically, environmentally, or morally. The project was shelved, but the concept remains one of the most tantalizing what-ifs in the history of space exploration. Other ideas push the limits even further. Solar sails, enormous reflective sheets pushed by sunlight, could accelerate gradually for years, eventually reaching thousands of kilometers per second. Laser sails, powered by beams from Earth, could send tiny gram-sized probes to 1% of the speed of light, around 3,000 kilometers per second. Such craft could cross the heliopause in 2 months, and the Oort cloud in a couple of years. The catch? These probes would be microscopic, not human-crewed starships, but messengers the size of chips. And then, the ultimate dream, fusion propulsion, harnessing the same energy that powers the stars. A controlled fusion engine could, in theory, reach speeds of 300 kilometers per second, or 0.1% of the speed of light. At that speed, a spacecraft could cross the heliopause in 2 years, and the inner Oort cloud in 30. That means, for the first time in history, we could leave the solar system within a human lifetime. But fusion remains one of humanity's greatest challenges. For now, it lives in laboratories, not in starships. Direction matters too. Earth moves around the sun at 30 kilometers per second. Any spacecraft launching from our planet inherits that motion. To leave efficiently, you must cancel some of it or use gravitational assist from planets like Jupiter to bend your trajectory outward. Without those boosts, the trip would take far longer, a humbling reminder that escaping gravity isn't just about speed, but strategy. In the end, the answer depends on which boundary you choose. Beyond the planets? A decade. Beyond the heliopause? 40 years. Beyond the sun's gravity altogether? Tens of thousands of years. The numbers are cold, but the story behind them is deeply human. Because each of those distances represents something we've already done, or someday will try to do. When Voyager 1 crossed into interstellar space, it became the first human-made object to touch the galaxy beyond. Attached to its side is a golden record, a message from Earth, images, sounds, greetings in 55 languages, and the music of Bach and Chuck Berry. If it's ever found, it will be a portrait of who we were. But it will never arrive anywhere. Space is too vast, and the stars are too far apart. Even traveling for billions of years, Voyager will likely never pass close to another star. And yet it keeps going, patiently, silently, as if declaring to the cosmos, "We were here." That's the real beauty of this journey. It isn't about escaping the sun's pull. It's about what drives us to try. Space turns our clocks into calendars, and our calendars into archaeology. The spacecraft we send today will still be traveling long after our mountains have eroded and our oceans have changed. They are our footprints in eternity. So how long does it take to leave the solar system? With today's technology, about a human lifetime for an uncrewed probe. To truly escape the sun's gravity, tens of thousands of years. But perhaps the more meaningful question is, how long does it take for us to decide that we want to leave? Because the boundary we're crossing isn't just physical, it's philosophical. It's the line between curiosity and fear, between staying home and venturing out. The solar system doesn't have a door that closes behind us. It has layers of wind, of gravity, of light, of time, and each one seems to ask, how far are we willing to go? Maybe that's the true time it takes to leave, the time it takes for us to imagine it, to build it, and to believe it's possible. If you enjoyed this journey, subscribe, turn on notifications, and tell us in the comments which impossible trip we should calculate next, the center of the galaxy, the Andromeda Galaxy, or the edge of the observable universe. Because as long as there are stars in the sky, there will always be another horizon waiting to be crossed. The distance to the edge of the solar system isn't just measured in kilometers. It's measured in ambition, in our will to reach beyond what we can see. And as long as that will endures, humanity will never stop moving outward. Because somewhere, far beyond the planets and the clouds of comets, two tiny spacecraft are still traveling. And through them, so are we.